Welcome everyone. If you're joining us for the first time, this is actually the second webinar from the Euclid project. Euclid aims to develop a curriculum for data practitioners with a special emphasis on linked data, and also to develop a lot of reusable training material, which is in part what's presented in these webinars. In this instance, what we'll focus on is querying linked data, and especially the use of Sparkle. In fact, Sparkle query and update. As usual in Euclid, if you have any feedback, if you have questions during this webinar, if you're watching live, or if you have feedback afterwards, please use the Twitter channel. So that's Euclid_project on Twitter. What I'll do today is present this webinar in two halves, and we'll take a look at the Twitter channel in the break between. Throughout Euclid, there's a motivating scenario based on building a music portal using lots of linked data, reusing web content, linked data, and we take different aspects of this architecture to focus on in different lectures. So today we'll be focusing on the Sparkle endpoint, and especially on how we bring together MusicBrainz data, which is a large data set of music, and DBpedia, which is a large general knowledge set of data, which is pulled as RDF from Wikipedia. So you'll see many of the queries and the updates today will use familiar DBpedia identifiers, which are used very frequently throughout the linked data world, as well as in-depth music knowledge drawn from MusicBrainz through an ontology, which we'll start to introduce today, and we'll focus on even more in the next module called the music ontology. So today, across the two halves of the webinar, we hope to reintroduce Sparkle, to talk in more depth about making queries over linked data using Sparkle. We'll give a very quick flavor of how those queries are executed, but mostly it's a view, we say a declarative view of querying, a say what you want rather than say how you get it view. We'll then talk about updating linked data. So Sparkle has evolved as a language from originally being one which was for query only towards one that's used for updates, so to change the data in a store. We'll give a quick overview to the protocol that's used in order to issue queries and updates. Again, we go into more data on that in Chapter 5, where we talk about APIs. And then finally, an important part, bringing together things that we've discussed before to talk about how one can take advantage of reasoning through a vocabulary, particularly an ontology, when querying. So having one's queries answered using inferred knowledge as well as explicit knowledge. Okay, so to reintroduce Sparkle, as I said, we have the stack of technologies developed for this idea of the semantic web, many of which are applied in linked data. And Sparkle sits over here, sits on top of RDF, so it's an RDF query language, or in full, a protocol, an RDF query language. And also, as we'll see in the second part of the webinar, it sits alongside things like OWL and RDFS, so those can be applied during querying, and will be in the examples that we'll look at. So, as I said, Sparkle, in the first instance, is a declarative, say what you want, query language for RDF data. And you can find a specification here. Underneath that, it has an algebra, which is related to the relational algebra that explains how, for instance, SQL, or you'll often hear me saying slightly incorrectly SQL. So the relational algebra explains how SQL queries work, in its first use. It also explains how Sparkle queries work over linked data, over RDF. A newer part of the Sparkle standards or recommendations, which are effective standards from the W3C, is the update language that says you have some store managing some RDF data, and you want to effect changes upon that data that's been managed. For that, you use the update language. Okay? In both cases, whether you're issuing queries or updates, you need some basic knowledge of this protocol to say how to issue your requests and see the results. Now, concerning the query part, and we'll cover both Sparkle 1.0 and the newer Sparkle 1.1 together, we have the basic query language over graph data with keywords for combining patterns, which are the means by which you express what data you want. We'll cover at the same time extensions that were introduced in the new language. So we can do things like aggregates. We can issue subqueries that are queries within queries. As well as updates, we'll touch only very briefly on a third extension, which is towards federation, where you say instead of having one store to whom you issue a query, you actually know about several stores and you want them to work together to answer your query. Now, how federation works and is applied is something that we'd really cover down in Chapter 5. Okay? So for the most part, we're talking about single queries and updates on a single store with all of the data. Okay, now the most important thing to understand when it comes to making the transition between snatches of RDF, which we've already seen, and queries over them, is to generalize from the idea of using Turtle to write down RDF, to make assertions, we'd say, to make statements, and building patterns that say, okay, someone has made assertions in RDF, and we're going to look for patterns within those assertions and within the inferences drawn from them if we're using entailment. So we generalize from this kind of pattern in Turtle, which is just an RDF triple. We assert that the Beatles, using a DBpedia identifier to identify them, the band, have the name according to some vocabulary, and we use the FOF, the friend of a friend vocabulary, and this literal on the end, this string of text which says the Beatles is the name for this resource representing the Beatles. Okay? That's a triple because everything is absolutely specified. We say the subject, the predicate, and the object, and make that assertion. In a pattern, we're allowed to use variables. So in any of these positions, subject, predicate, object, or we'll see in a second graph, we can say, I don't know. I'm not asserting that. I want the store to tell me what can match here. So in a simple case, we could say the Beatles, again, using the DBpedia ID, made, according to the FOF vocabulary, something. Okay? When I use a question mark before a name, or equally I can use a dollar mark before the name, it says, I don't know, tell me. Tell me what triples you have that could match this pattern, where the Beatles made something. And the essence of query answering is finding bindings for this variable. So saying what resources can match this variable. Now, when we extend that with multiple triple patterns, we can reuse the variable. So we say, for instance, that that album, using the same variable, has a track according to the music ontology, about which more later. And again, we don't specify what track it is, we ask. Okay? We can generalize even further. So here we've got variables in the subject and object position. Here we also have a predicate. So we say, with variables for all of these, but under the condition that the same binding is made for album across all of these patterns, we say, for those albums that you found, tell me essentially all of the statements where that album is a subject. Okay? So no matter what the relationship is or what it's related to, tell me all of these relationships forward from the album. So tell me about the album. Okay? Now finally, as promised, these are triple patterns. We can also have quad patterns, where the fourth part in the quad is the name of a graph where the triple is stored or where it's asserted. Okay? So we can either be explicit about the graph, so we use a name for the graph and ask for triples inside it, or we can use a variable in the graph position. We can say, tell me in which graph there are triples that match this pattern. Okay? As I said, that's the essence of making queries across RDF in Sparkle, and we're going to look at several examples now and several ways to combine these patterns into the richer language, which is Sparkle. Now, a bit of background. As you will have seen, have you watched the first webinar or read the first chapter as an ebook or online, when we make statements using RDF triples, they can be combined into a graph. So every relationship between resources becomes an arrow in a graph, and the nodes in the graph, the points, are the resources whose relationships we're modeling. Now, a data set, which is what a store manages, is actually made up of several graphs. So if we put things into named graphs, you have triples within those named graphs. What it also has is one default graph. So you have triples who don't have a named graph as a container. Now, in general, we'd like to avoid putting things in such an ambiguous context where you don't know in which graph they belong, and therefore you can't make statements about the graph to add information, we say provenance information, about a container full of triples. But as we'll see when we look at entailment later, even if we don't put things into the default graph, it's still a useful place to look for data, to match data, because in a standard implementation, this default graph will be where we put inferred statements. Okay? So we store explicit statements, hopefully in named graphs, and from the combination of those statements, together with the vocabulary, which is a schema or an ontology, we can infer further facts that weren't explicitly asserted. The place to look for those in a standard implementation is in the default graph of the store. Okay, now the other roles that we need to know about in querying are you have a client to the protocol, the person issuing a query, or later we'll see an update. You have the service that provides the endpoint where the client issues his query or his update, which is provided by the store normally. And, okay, as I said, that service is providing at least two endpoints, at least a query endpoint and an update endpoint. We'll see later in Chapter 5 that, in fact, we can make that finer grained and give an endpoint to each named graph to manipulate them separately. But for now, we think about just two endpoints, a query endpoint and an update endpoint, across this data set, which is made up of several graphs, most of which have names, and one doesn't have a name, called the default graph. Okay, so on to querying. The pattern that we just saw, where we wrote essentially what looked like a triple, but we used a variable in the object position, is a triple pattern. And just as we can draw a triple as an arc in a graph, we can draw a triple pattern as an arc in a graph. So we have the Beatles made, okay, subject, predicate, and the object was a variable. So it's like a hole in the graph. We're looking through the data set to say, where can we match this kind of pattern by overlaying this? And when we do, what fits in the place of album? We say binds to the variable album. And that binding is the basis on which we form a result to the query. So if we take this data, which is related to what you'll see in exercise and the exercises for this chapter, okay, a subset of that data looks as follows. Okay? We have a resource to represent the Beatles. We have some relationships through this FOF-made relationship. Okay? And those resources come from MusicBrainz, come from this representation of the MusicBrainz data set in RDF. Okay? Attached to those resources, we have relationships in the property title from the Dublin core vocabulary. So we give labels to these things with title, okay? And that actually helps us to understand. Here we're talking about the album Help, the album Abbey Road, and the album Let It Be. Okay? Now, if we take this pattern that we were just looking at and match it on top of that graph, you can probably see how it fits. Take that and match it here, and we get a binding of this for album, which goes in the first row. We have another match here, where this album binds for album, and a third one there. So we get a table full of 3 results for this column album representing the variable. It's very useful, but we'll see there's a couple of gotchas in a second. Okay? The first question that I want to ask before we even look at the query forms is, what do we want to return? Okay? It makes a big difference whether we're talking directly to a human or whether we're talking to a machine that's interpreting these results for a human. Okay? A machine might be perfectly happy to just get back these URIs identifying those resources, because in common with linked data, those are HTTP URIs that we can resolve. So if the machine wants to know more, it can just ask, what's the RDF description of what this URI represents? Okay. So a machine might be quite happy to get this table full of results. A human, on the other hand, actually wants to know that this is help, Abbey Road, and let it be. So they may be more interested in the labels, for which reason we might extend this pattern to include a second relationship. We don't just say we want something that was made by the Beatles, the album, but we want a second pattern where the album is the subject, the relationship is title, and we want to know what binds to title. Okay? So we can play the game again by comparing the data set with the pattern and see that again we've got 3 matches down this branch, down here, and down here, but we've got 2 bindings for each of those matchings now. Okay? So in the first case, this is the album, and that's the title. In the second case, this is the album, and that's the title. And third case, we have this match. Okay? Important to realize that because we used album twice when we write these down as triple patterns, once as the object of this relationship, and once as the subject here, we can't take this apart and just say, can we have 2 matches? Okay? It's got to be a match for this whole chain where the same thing stands for the object of this relationship and the subject of this one. So we have the same midpoint. Okay? Again, we can do it here, here, and here. Okay? So when we look at query forms, we'll see when we have such a binding set over at the bottom right with bindings for album and bindings for title, we might choose to have both of them, so the right combinations of these 2 things, so a human can read the label, the title, and the machine can interpret the resource for them, or we might just project down to the title because really we're just displaying something that needs no further interaction. Okay? So the important part of the query is saying, once you've matched the pattern, what do you want back? How do you want to interpret this table into some results? Okay, one further gotcha. If I just change which portion of music brains I have in this data set as follows, you'll see there's a bit of ambiguity and a real gotcha in the way that the query is written. Okay? The way the music brains data set's constructed, the Beatles made the album Help, but they also made the track called Help, which is the first track on that album. Okay? Now the model is rich enough that we can distinguish those 2 things, because we also have a relationship where this is in a class called track, and this resource is in a class called record. Okay? You hopefully remember that the label for these relationships is RDF type, which we can also write A. Okay? In Turtle and equally in Sparkle, we can give a shortcut for RDF type, which is just A. This is in that class. Okay? So we could equally extend our pattern that just said the Beatles made the album to say the Beatles made this resource, and this resource is in the class of records, which are one view of what album means across music brains. Okay? If we didn't have this pattern, then this first pattern that we had, the Beatles made a resource, could match both here and here. And this is what I meant about a gotcha. We might, in writing the query, use the variable name album, but we could have used any other name. We could have used ? Barry, We could have used question mark Euclid. Okay? It has no effect on the semantics what we name the variable. So if we write a pattern that says the Beatles made an album, okay, we can equally bind to that variable called album a track, or indeed the Beatles made movies. Okay? So the naming of the variable has no effect on the binding. If we want to say that the resource that should be bound here belongs to a class, we add another pattern that says that variable is a resource that's in the class that we're interested in. Okay, now in terms of turning these patterns and bindings into results, we have several options in Sparkle. The first one is what's called a select query. Okay? A select query actually gives back a table. So it's very easy to derive this table full of bindings into a table result for a Sparkle query. The way that we write the query is to start with what we call a prologue here, which is probably quite familiar from Turtle. It's a bunch of prefix definitions for namespaces. Okay? Important point to note is that syntax is subtly different from Turtle.